routing, or how we connect our network islands.
It's a bit of a paradox, isn't it? In networking, we spend so much time and effort building these digital walls to keep things separate for security and organization. But then, those separate groups actually need to talk to each other. So how do we do that? Well, that's the puzzle we're going to solve.
Okay, first things first, a quick refresher on what a VLAN even is. The absolute best analogy is an office building. We put the marketing team on floor 10 and the engineering team on floor 20. Now, they're all in the same building, plugged into the very same physical switch, but they are completely isolated from one another. This is fantastic for security and for keeping all that network chatter contained. But here's the inevitable problem. What if someone from marketing needs a file from an engineer? By default, nope, can't happen. It's like the elevator doesn't go between those two floors. Their networks are two totally separate islands. So to build a bridge between these islands, we need a router. And that whole process, that's what we call inter-VLAN routing. Let's look at the different ways we can pull this off.
First up, we've got the most straightforward old-school method, the physical approach.
The logic here is dead simple. For every single VLAN you have, you use up one physical port on your router and run a cable down to your switch. In our office analogy, this is like building a completely separate private elevator for every single floor. Sure, it works, but I'm guessing you can already see the major problem with this approach.
You know, the beauty of this method is its sheer simplicity. It's incredibly easy to understand and set up. But the disadvantage is an absolute deal breaker for most modern networks. If you've got 20 VLANs, you need 20 expensive router ports and 20 cables. It just doesn't scale at all.
And the configuration reflects that simplicity. You're basically just looking at this one line of code. You assign an IP address to a physical port, and that port becomes the official doorway or default gateway for every device in that VLAN. Simple, yes, but very heavy on the hardware.
So how do we fix that massive scalability problem? Well, that brings us to a much more elegant and clever solution, famously known as router on a stick.
Now, instead of needing 20 ports and a mess of 20 cables, we use just one. A single physical link connects the router and the switch. We configure that link as a trunk, which is just a fancy way of saying it can carry traffic for lots of different VLANs at once. Then on the router, we create these logical sub-interfaces, one for each VLAN. So we've basically replaced our 20 separate elevators with one big smart elevator that knows exactly which floor to stop at.
The advantage here is pretty obvious. It's incredibly scalable. You can have dozens of VLANs all running over one connection. The trade-off, though, is that this single link can become a traffic jam. If marketing and engineering start sending massive files back and forth all day, our one smart elevator is going to get really crowded and everything slows down.
And how does it work? It's all about this command right here, encapsulation.1q10. This is what tells the router to tag any traffic from this virtual interface as belonging to VLAN 10. That tag is exactly like the floor number on an elevator button. It tells the network precisely where that data needs to go. Now, router on a stick is clever, no doubt, but modern networks demand speed. And that leads us to our final and fastest solution, taking the router out of the equation almost entirely. This is where we bring in a layer 3 or multi-layer switch. Layer 3 just refers to the routing layer of the network. So what we have here is a device that's both a switch and a router all rolled into one. It does all the routing internally at lightning speed. So instead of an external elevator, we've just built high-speed escalators and stairs right into the building's foundation. Communication between floors is now seamless and incredibly fast.
The advantage is just pure, raw performance. There is no external link to become a bottleneck. Everything happens at the switch's internal backplane speed. The only real disadvantage? Well, as you might guess, these high-performance combo devices, they do cost a bit more than your standard Layer 2 switch.
The configuration is also beautifully simple. With this command, we create a logical interface, called a Switched Virtual Interface, or SVI, directly on the switch itself. Then, we assign an IP address to it, and just like that, the switch itself becomes the gateway for that VLAN. No external router, no sub-interfaces, just pure, integrated, high-speed routing.
So let's put it all together. This table gives us the perfect summary. Physical interfaces? Simple but low scalability. Router on a stick? Highly scalable, but you have that single trunk link as a potential bottleneck. And finally, the multi-layer switch, which gives you high scalability and the absolute best performance, limited only by the speed of its internal hardware. Now, here's a really cool pro tip for you.
You might be thinking that you need to go out and buy an expensive Layer 3 switch to get that top-tier performance. But some very common Layer 2 switches, like the super popular Cisco 2960, actually have basic routing capabilities hidden inside. You just have to unlock them.
And it's surprisingly easy to do. You just change something called the Switch Database Management, or SDM template, with one command. You're basically telling the switch to reallocate its resources for routing. Give it a quick reload, and suddenly your Layer 2 switch can create SVIs and perform basic Inter-VLAN routing. How cool is that?
So what's the final takeaway from all this? For any modern network that needs speed, scalability, and efficiency, using switched virtual interfaces on a multi-layer switch is, without a doubt, the industry standard. It's the most robust and efficient way to connect your network islands, period.
And that leaves us with one final thought. We've watched the whole function of routing evolve from a clunky external box to a feature that's deeply integrated inside our switches. So the question is, what's the next step in that evolution? Where does routing go from here? Thanks for watching.